Why do people go bald?
Why are baboons' bums red?
What's a light year? Why do leaves go brown in the autumn? Why do monkeys like bananas? Why do some things glow in the dark? Why do animals not understand humans? Why do my receipts fade after a year?
Don't know the answer? Ask the Naked Scientists.
Hello and welcome to this week's Ask the Naked Scientists with me, Sue Marchant, and Dave Ansell. Right now, let us welcome into the studio the one and only Dr. Dave from Ask the Naked Scientists.
Good evening.
Good evening, Dave. Now then, of course, it's all been in the news, science this week, and, you know, people with white coats. What have you got to report for us?
Well, I guess the big story of the week is the Large Hadron Collider in CERN. This is a huge physics experiment. Actually straddles both Switzerland and France. It's so big it crosses borders of countries. It's a 27-kilometre diameter ring. What they're doing is trying to find out some really fundamental questions about the universe. Things like, I don't know if you ever noticed, you've got a heavy shopping trolley, something like that. You push it, it's hard to start it moving, and once it's going really fast towards a pile of whiskey at the end of the aisle, it's really hard to stop it again.
Yes.
Everything, mass has this property called inertia, which makes it hard to start things moving and hard to stop them moving. And physicists know about this. We can write it down very accurately as to how it behaves, but don't really know why it's there. All of our best theories don't really explain why it's there. And there's a couple of hypotheses which might be one of these things called a thing called the Higgs boson, which an Edinburgh-based physicist came up with in the 70s, I think. But no one's actually been able to test this theory, so they're trying to find out whether he's got it right or whether there's something else entirely weird going on. And various things like there's two types of matter called matter and antimatter. They come together, they explode in a huge ball of energy. And we don't really know why there's so much more matter than antimatter. According to all of the explanations at the beginning of the universe, there should be about the same amount of each, but there's far more matter than antimatter. And so they're trying to look at some very subtle effects of the way the universe works, which might mean there's more matter than antimatter.
Gusser says that he hasn't followed the Large Hadron Collider story. Have they simulated the Big Bang, and have they discovered anything of earth-shattering importance for all that money? Because they're doing a series of experiments, aren't they?
Yeah, the way that the experiment's working is they're taking protons, which, I don't know if you remember at school, atoms are made up of lumps, nuclei in the middle, and then little electrons flying around the outside. Yep. One of the things which can make up the nuclei are called protons. These, you can also get neutrons as well, but in the Large Hadron Collider, they're taking protons, and they're charged. So they apply an electric field to them, like charging up a balloon. If you put a charged balloon near a proton, it will fly towards it. So they're applying electric fields and making these protons accelerate round and round in circles, faster and faster and faster. They get up to about 0.999992-ish of the speed of light. So almost as fast as you can possibly go, and then smashing them into each other. They haven't actually started smashing them into each other. They haven't actually started accelerating them as fast as they've gone. But what they were doing this week was basically putting the first protons into the ring and starting to accelerate them. It's a huge, immensely complicated machine, and when you start using one of these things, you don't just turn it on and it works. You turn it on, you fiddle with some controls, you try and get it to go a bit fast, you fiddle with some more controls, you find it's veering off to the left, so you play with some more controls. So it's probably not going to start really powerful collisions until sort of April next year.
All right, OK. And then in that case, the James Bond team will be standing by for him to save something. So, Gus, no, they haven't sorted it out yet, but it'll be over a matter of time. Now then, Andrew from Cambridge has a question. He says, Dr. Dave, regarding the Collider, I understand the detectors stand 11 stories high. Is this true? Also, what is the way that they work?
Yes, there's various detectors in the Large Hadron Collider, each one designed for looking at different things, and some of them just designed for looking at various interesting things. Some of them are 11 stories high. They're absolutely immense, weighing thousands of tons. There's various different types of detectors. Basically, in each experiment, there's various different types of detectors. There's various ways of detecting particles. One of them is that if you have a particle, it's going at 0.999999 times the speed of light. It then goes into a material. And in fact, in the material, light doesn't go as fast as it does does in the outside world. And actually this particle is now going faster than the speed of light in that material. What you get then is a bow wave, like a bow wave from a boat. But instead of sort of ripples on water, you actually get light given out. You get sort of a light given out from the bow wave of this particle, and you can detect that. So some of the detectors are designed will sort of pick a track of a particle moving through the detector by looking for the light it gives off. Other ones are designed to actually stop the particle. They're called calorimeters, and so they're a big lump of something probably quite dense. I'm not quite sure. Something with a very large mass like lead, and then you measure what the change in temperature of that lump of stuff from the particle hitting it. You cool it down to incredibly low temperatures so you can measure the differences much more accurately. And then they put thousands and thousands and thousands of these detectors very carefully arranged. They also apply magnetic fields, because if you apply a magnetic field, then a charged particle will go around a corner. This is how your old-fashioned TV works. You fire electrons in from the back of a TV. They fly forwards, then you apply magnetic fields to it, and it sort of steers this beam of electrons across the front of the screen and builds up a picture. And so you can apply magnetic fields to your machine, and then charged particles will get bent, other ones won't, so you can start to tell the difference between particles. And you can have some things stop some particles, not others. So by knowing where the particles go and knowing the properties of detectors, you can start to work out what they were.
Way above my head, it really is now then. Dr. Dave, fantastic. Gerald has sent an email in. Cheap energy that is non-polluting is the holy grail for power generation. Technically, there are many lines of research that could produce this, but traditionally little is invested in them compared to that which produces nuclear waste. Is fission power feasible? What looks promising for green energy? What are the current lines of research? That's from Gerald.
I'm guessing he means fusion power rather than fission, because fission power is how nuclear power stations work at the moment, and they do produce quite a lot of nuclear waste. There's a debate as to how much that is and how dangerous it is, and whether it's worth doing or not. Basically, there are lots and lots of technologies which are getting to the point where they're just about marketable, and if energy stays expensive the way it is, I'm absolutely sure that lots of them will suddenly become... Suddenly people can make money by building power stations. If you make money making power stations out of solar power or wind power, then everyone's going to do it and make lots of money. But that means we've got lots of solar power and wind power and non-polluting forms of electricity. So solar power is a really big one, because an absolutely immense amount of energy comes onto the Earth from the sun. So that's a really big one. Wind power is still working. Yes, there's lots of things which are going to be there, but give it some time.
Dr. Dave, we have, I believe it's Ted on the line. Hello, Ted.
Good evening.
What's your question?
I've always been fascinated when you yawn, and I ask the question is that when you're tired, you tend to yawn, but that's not always when you yawn. But the second part of the question is, when you somebody in the party actually yawns, why do you copy it?
Yeah,
nice question, Ted.
Not right on my area of expertise, but I can try and say something which might be useful. Yawning, certainly, sometimes when you're short of oxygen, you can yawn because you can sort of get a lung full of air into your lungs. Right. So sometimes people start yawning if they're sort of they've been sitting around not breathing enough, and all of a sudden they need to have a deep breath of air and get a bit more oxygen into their bloodstream. But I'm not convinced that that's entirely what's going on because of the way that it is infectious. And I don't think it's just infectious with humans. I definitely know when I grew up we used to have a dog, and if you'd yawn, she'd yawn too. And also hunting dogs in Africa. I remember seeing a programme whereby when they're about to go to bed, one dog will start yawning and the other ones will start yawning and they'll all start yawning and then they will curl up and go to bed. So my best bet is that there's some kind of intrinsic reason why you might yawn. I'm not entirely sure about that because I'm not really a medic. Right. And if you're tired, And then it's been used over the years for groups of animals and then humans, that for everyone to decide to go to bed at the same time, because otherwise, if you've got a group of dogs who want to go out hunting at a certain time in the morning, and some of you went to bed at 5 o'clock in the afternoon, some of you went to bed at midnight, then a load of people being dragged out won't want to get up at the right time, your group won't be very cohesive because not everyone's going to be up, so you won't all be able to go and jump on the wildebeest or whatever.
Right.
And so I think it could be something to do with sort of social interactions and making groups of animals and people sort of decide to go to bed at the same time, so then they'll get up at the same time.
Dr. Dave, we have another one here from Gus. He says, there is still a lot of coal in Britain. Can it be made into a viable, clean source of energy?
There is a lot of coal in Britain. I've heard numbers like sort of 100 years or a couple of 100 years worth. If you just burn coal straight away, it produces a lot more carbon than other ways. It's about the dirtiest way of producing energy because it is pure carbon. So, whereas if you burn gas, there's both carbon and hydrogen in it. It's a hydrocarbon or oil. Some of the energy comes from burning hydrogen, which produces water, which is perfectly reasonable, which isn't a problem to the world at all. And some of it comes from the carbon in the hydrocarbon, which is a problem. So coal is definitely worse. There are all sorts of ideas which involve basically taking the carbon dioxide from which you've burnt and then pumping it down an old gas well. So if you have a power station somewhere near the North Sea, you have an empty gas well under the North Sea, you then basically just pump the carbon dioxide down the well and it will sit there as a gas, and then it's probably not going to escape for tens or if not hundreds of thousands of years. There are other plans involved. If you've got a rock which is very alkaline, like a basalt or something, if you pump carbon dioxide down into that, when carbon dioxide dissolves in water, it forms carbonic acid, which will then react with the alkali basalt and form carbonates, a bit like limestone. And then that really will be locked up for a long time. So there are definitely ways of making it clean. It's just whether they end up costing more than using another form of just putting up wind turbines, which to me feels like a nicer way of doing it. But we'll see what happens.
Another Dave is on the line. It's Dave in Bradwell. Hello, Dave.
Hello, Sue.
What's your question for Dr. Dave?
Yeah. It's something what's really concerned me for quite some many years. You're on your own, whether it be in your garden shed, in your garden allotment, in your house, but you're on your own. And then for some reason, you flick round and your husband, your wife or somebody is there behind you, a friend. But there's no noise, but for some reason you turn around and you find that you're not on your own. What do you think? Dormant, sixth sense, or what?
My feeling is that it's probably less about being sort of something supernatural and more about the way your brain works. Because although it feels like there's sort of only one person in your head, it's actually incredibly complicated. There's a sort of conscious bit, which is what you think is you. And there's all sorts of subroutines going on in the background, which are doing things like, if you just envision is incredibly complicated. There's actually special bits of your brain designed for recognising faces. And if someone has that bit of the brain damage, they can't see the face. And you can actually have some types of brain damage where visual information can get through to all of these subconscious subroutines, but it doesn't get to the conscious part of your brain. So people don't think they can see anything at all. But if you give them a post and a letter and you put a post box in front of them, and it could be the horizontal or vertical, and then tell them to imagine a post box and post a letter through it, they can do it automatically.
Exactly.
Because there's all these subroutines. So what I would have thought is going on is, although your conscious brain isn't aware of subtle signs like hearing breathing or little footsteps or something, there's a subconscious part of your brain it's very useful evolutionary to have a piece of your brain which is always sitting there listening for something which might be creeping up on you, because it might be a saber-toothed tiger. So I think it's just that consciously you haven't heard it, but subconsciously you have, and then all of a sudden it's knocking, saying there might be something behind you. Have a look round.
Thanks for your time.
Thank you, Dave.
All right.
Bye-bye.
Bye.
Dave, an email this time from Pierre, listening in Montreal, in Canada. Good evening, Pierre. He says he was wondering if to make something rise in the air, it needs to be of a lesser density than air. Would it be possible to build a super light, super strong container, create a vacuum inside and make it rise in the air? Or would it simply be crushed by the atmospheric pressure? Dr. Dave.
Theory is wonderful. Basically, the reason why balloons float, in fact, anything floats, is that they're less dense than the stuff around them, so that they get an upthrust. And the bigger the difference in density between what's in your balloon and what's outside it, the bigger the lift you get. And so the biggest difference you can get is from something with no density at all, a vacuum, compared to air around you. The problem is that the strength of the container to hold back the pressure of air needs to be absolutely immense. And the weight of the container are built vacuum containers, and they do actually have to be quite thick just to take the pressure. And I don't think you'd ever manage to make one light enough to be able to hold back atmospheric pressure. Whereas if you compare that to helium or hydrogen, which is the lightest gas you can get, which is only about 1/14 of the density of normal air, so about sort of 7% of it. Hydrogen can push back against air pressure perfectly happily, and it doesn't work without having to build a strong material. All you need is just a simple thin envelope to hold it in. And you're not actually going to gain very much in lift between a vacuum and hydrogen, because you're only playing with that last 7% of the density of air. So it's almost certainly not worth it, although in theory it would work, and unfortunately in practice I don't think it would.
Right, thank you very much indeed. Another question this time coming in by email from Bruno Satino. Great name. Bruno says, why does kitchen foil, aluminium, never get hot no matter how long you leave it inside a hot oven? I know aluminium stops radiated heat energy being transferred, but being a metal, it should get hot. Does the thickness of the foil have anything to do with it? Great question. Thank you, Bruno.
Yes, I think he's got it in one there. If you put an aluminium spoon in an oven and you took it out and you touched it, you would burn yourself very quickly. Aluminium conducts heat exceedingly well. If you have an awful lot of heat energy dumped into your finger very quickly, it would probably boil the water under there and it would hurt like anything. However, aluminium foil is incredibly, incredibly thin. So first thing is there's very little energy stored in it because it's so thin. So when you take it out of the oven, it's going to cool down very quickly. But even if it hadn't cooled down by the time you touched it, just touching the very top surface of your finger is probably going to cool it down to a temperature which isn't going to harm you very quickly, and there's not enough energy gone into your finger to heat your finger up to the point where it will burn, so it doesn't hurt you. So it's not really to do with the fact that aluminium is very shiny, so it will reflect infrared light, so it's a good insulator, which is why I get the space blankets. It's more to do with just the fact that it's so thin. If you touch anything very thin, it's probably not going to have enough heat energy in there to damage you.
On the phone, we have Jim, who's from Mablethorpe. Good evening, Jim.
Hello, Sue. Nice to speak to you again.
Thank you. You're through to Dr. Dave.
Lovely. Right, Dr. Dave, could you possibly tell me how or why boats, when they seem, or ships I should say, when they seem top-heavy, don't topple over?
Why, when they seem top-heavy?
I'm looking at one at the moment, and it seems most of it's out of the water, and it's fully loaded, and yet it's still upright. It just baffles me how it works.
One thing which they do is put a lot of heavy stuff low down and light stuff high up. So there'll be a lot of, definitely old-fashioned ships, they used to put a lot of pig iron right down, as far down as they could, which means, because with this ship, you get the centre of the buoyancy and the centre of the mass. And if the centre of mass is above the centre of buoyancy, you can release energy by turning over and turning upside down. Whereas if it's the other way up, then it's a bit like a pendulum trying to stand up upside down, and it tends to fall over. But if you've got the mass below the centre of buoyancy, then it will always stay the right way up. Depending on also on the shape of the ship, things like a catamaran, because it's so wide, you can have the centre of mass above the centre of buoyancy, because in order to turn upside down, it's got to completely submerge one hull, and that's never going to happen. So normally things that are high up, things like masts and superstructures, are full of air and aren't very dense. Despite the fact they look very big, they're not very heavy, and all the stuff underwater is where you keep all the heavy engines and lots of ballast, pig iron and things.
It just seems a bit of an illusion, because, I mean, there's all these lorries I can see it's on this ship. There must be 40 or 50 lorries on the top. There must be a hell of a weight below the waterline then.
The other thing is that if you compare something like a car or even a lorry to something solid, even grain, something which fills up all the gaps, there's an awful lot of air inside a car or a lorry.
Yeah.
And so it's not, although it's maybe 40 tons, it actually takes up a lot of space. So by ship standards, it's not very heavy. So if you filled that space up with iron ore, then you'd be talking probably 300-400 tons of iron ore in the space of a lorry. So compared to the pig iron at the bottom, it's probably not that heavy.
Right, thank you very much for your help.
Cheers, thanks.
Thanks very much. Bye-bye now.
You're welcome. Bye. Now, coming up next, we have another email, Dave. This time it is from somebody concerned about the CERN. Tarquin says, the UK has put £500 million into CERN, which seems rather small. Who else has contributed and how much? Listening to the UK news, we hear that British scientists are taking a leading role in the experiment. How does that hold up with the minimal UK investment?
£500 million is probably about 10% of the cost so far, which is much less than half of it, but it's still a fairly major lump. The biggest contributors are the European Union, all the states in the European Union, and I can't find any actual direct figures. I can imagine they're not necessarily advertised everywhere because these things are not. There's an awful lot of politics with this sort of thing. But I would have thought it probably goes with how rich the countries are. So I'd have thought that Britain, France and Germany had similar sort of contributions. And then there's a whole of the rest of the EU. Then there's definitely been contributions from America and Australia and basically all the countries which are interested in this sort of thing to varying degrees. 20 countries in the European Union. And then there's another, apparently there's at least sort of over 100 countries, physicists from different countries involved in it. So whilst it's nowhere near half, I could imagine that it was one of the biggest contributions.
Excellent. Thank you, Dave. And I'm pleased to say, let's say a very good evening and welcome to Tony. Hello, Tony.
Good evening, Sue.
What's your question for Dr. Dave?
Well, it's rather hard to explain, but the Earth goes round the sun, so therefore it rises and sets. But I can't quite understand how the moon, as it were, keeps in sync, because that's going round us, and we're going round at the same time.
Yeah, you're right. The Earth is going around the sun, and the moon is going around the Earth.
Yeah.
But the moon is going around once every 28 days.
Yeah.
So in terms of a day, the moon is essentially staying in the same place. It's going so slowly, it's not really moving very much. So the Earth, because the Earth's spinning so fast under it, the moon moves across the sky at about the same speed as the sun and the stars do. But as the month goes on, the moon is moving an appreciable distance. So so it will rise at different times because it's in a different place, and it will set at different times. And also because if it's between us and the sun, then the side which is lit up by the sun is pointing away from us, so it looks dark. So you get a new moon. If it's beside us, then you can see half of the moon which is lit up and half of it which isn't. And if it's the opposite side of the sun, then you'll see the lit up side, so it's a full moon.
Oh, that's interesting. I've got the idea, yes. Thank you very much, Dr. Dave.
Thanks very much, Tony.
We've got Robin on the line. Good evening, Robin. You're through to Dr. Dave.
Good evening, Sue. Nice to speak to you again.
Thank you.
Hello, Dr. Dave.
Hello.
Yesterday I've been looking through the Daily Mirror today, and on page 2 there's a photo of a giant iceberg off the coast of Newfoundland.
Yeah.
And it was saying they can be 15,000 years old, as high as a 20-storey building, and weigh more than 10 million tons. Now, how do they know the weight of an iceberg?
I would have thought the way they do it is that ice, you know roughly what you know what ice is made of. You know roughly its density. So if you put a lump of ice in some water and you look at how much of it is floating above the surface of the water, if you can somehow measure the volume of the ice which is above the surface of the water, then you know that there's, I think it's either 9 or 10 times more of it under the water as well. So you can then multiply that figure, the volume, by 10 to know the volume of all the ice. And if you know how much a cubic metre of ice weighs, which is probably about 900 kilograms, you multiply that up by the volume of the iceberg, which you just worked out, and you should get a figure for how much the whole thing weighs.
in the picture, it shows you as though it's on a sunny day. So I'd have thought with the sun, it melts so much of it. So wouldn't that bring the weight down a bit? As
it melts, then the weight does definitely reduce, and it gets smaller. Although melting an iceberg, definitely just from the sun, will take a very long time because, first of all, it's white, so at least 90% of the sunlight will get reflected straight off, so it's not going to be heating it up. The other thing is melting water requires an immense amount of energy, so it'll take a very, very, very long time.
I was just wondering how they measure the thickness of it as well, because looking at it, there's a thick piece and then like a U shape, and then there's another small bit on the end of it.
Yeah, I don't know whether that one specifically they have measured in great detail. I mean, you could probably use side-scanning sonar, which is sending pulses of sound sideways and listening to where they bounce back from, and you get a good reflection off a piece of ice. So that would be one way that they could be doing it.
And would that make any difference to the sea level at all?
If the iceberg started off floating and it melts, then it should make very little difference to the sea level at all. However, because if you take because the amount of water that the iceberg produces will be almost identical to the amount of water that it was displacing. Because of the rules of the way things float. However, if the iceberg, if a lump of ice starts off on land, so something like the Greenland ice cap or Antarctica, if that falls into the water and melts, then that will raise the sea levels.
That's it for this week. Our doctors will be back with me next week for more Ask the Naked Scientist. But don't forget, you can also catch them on the Naked Scientist podcast, which you can find on the Naked Scientist website, www.nakedscientist.com.
The Naked Scientists are sponsored by the Wellcome Trust, the EPSRC and UK Fast. For more information, look us up online at nakedscientists.com.